Hello everybody, this is Sandeep here. Welcome to 12W12M series where we are going to conduct the 12 webinars in 12 months. This is the series in which we are upgrading the awareness of the civil engineering candidates. In this webinar, what is the topic that we have come up with? This topic is extremely important from the civil engineering point of view, specifically from the analysis and all. The topic is the structural analysis. All right, during the last session, if you know that, we have studied many things about the modeling types. So I'll just get started, right? So if you see here, you can see that we have studied the different types of grids. Like say, for example, we are having the floor grids, then plane frame, space frame, the floor grid analysis, and many things we have studied during the last the session. In this particular session, we are going to study the analysis topics, right? So what are the different types of analysis are there? I have elaboratively given all the different types of analysis possibly that I can explain you during this session over here, right? This particular, these are the only types of analysis? No, there are varied variety of analysis is there, right? Basically, what do you mean by analysis? Analysis is like, let's say for example, you give certain loads and the stiffness actually and try to calibrate that whether the member is buckling, whether the member is bending, whether the member is failing under the shear and all actually. And there is a linear static analysis that everybody knows, and that is generally calculated during the college days actually. If you take the simple line diagram actually, let's say for example, if this is the case, right, you are having certain load here and this is the length actually, and this is the W, okay, the WL square by 8, okay, so that is the bending moment diagram, right? So if you see that, whatever the determinate and indeterminate structure, the structure becomes a little complex actually if you are having something like this. If let's say for example, if you are having something like this where this is the fixed supports, right, the structure becomes even more complex if you are having something like this. The structure becomes even more complex actually if you are having something like this, which is the space frame analysis. All right, so we have studied during last time actually when it comes to the individual line beam line element. All right, and we have also seen the plane frame and the space frame, but we are not going to discuss about the different types of portal frames and all in this particular topic or in this particular session. In this particular session, we are going to study many things about the different types of analysis and the college days, what we have studied, and in reality, what all the different types are there, right? So let's get started. First is the linear static analysis. Linear static analysis, what is that? You are having the, basically, you might be knowing this diagram, okay? The stress versus strain, it is linear curve, but when it goes later on actually, it goes to the non-linear analysis, because this cannot be determined. Something like this over here, if it is a steel, there is a different curve. If it is a concrete, there is a different curve and all actually. We have studied during last, so many years during the college days. So basically, this is a complex equation. So we don't consider this. So we make sure that, the structure lies within this particular zone. But is this the only reason that we go for the linear static analysis? No, there are various reasons. One reason is actually the complexity, right? Complexity. What do you mean by complexity? If you see the linear static analysis, you know the input parameters, you know the input equations, and you know the output variables and their determinate behavior. So it is not indeterminate structure, it is a determinate structure. Right, so it is very, very simple. The complexity doesn't exist. All right, so and it is very easy to numerically solve certain equations. Right, so it is easy for any particular student to calculate through the calculator or through the logbook, logarithmic books and all actually, and get the answers very easily. But in reality, do all these things helps us? Okay. So the real answer you only need to tell me before we finish the session. All right. So if you see that, what is nonlinear analysis? Let's look into the nonlinearity option. All right. So what are the different nonlinear options are there? If you see that in the static analysis only, we are having the nonlinear option, which is the geometric nonlinear, we are also having the material nonlinear option. In the geometric nonlinearity, we are having the P delta analysis. P delta, buckling, pushover, creep, shrinkage, material. Okay, in which the geometric nonlinearity will be having only P delta, buckling and pushover. In the material nonlinearity, we are having creep, shrinkage and material strength. What do you mean by the nonlinear analysis? And these two types are what it is. So let's say, for example, we are having some cantilever here, and you will see that whenever you are applying the force, it is going, this is the L, and you will see that L plus delta L. Some particular length will get increased, obviously, because of the elongation of that particular member. The moment you reduce or delete this force, it will regain its original position. All right. So that is necessarily the static and linear behavior. Right. But the moment you are having delta L, it is no more a linear, it becomes a nonlinear, and it is having a geometric nonlinear behavior and having a delta effect. Why? Because this is delta. You can take this as a delta 1. Right? What is delta 1? Is the deflection between this and this. So whenever any element you are considering, okay, you are taking some horizontal forces above it. So let's say I'll delete this and I'll redraw it with the pen like this over here. So if you are having horizontal force, let's say P here, and you are having delta here, this is the delta effect. So it's not only the horizontal force or something. Sometimes, you will be having the same problem with the vertical force. Why? Because you might be having some kind of, architectural designing problem. So let's say, for example, if this is the building, you are having, this is the center of mass, and you are having, this is the center of stiffness, which is center of rigidity. Some people, they call it as center of stiffness, some people they call it as center of rigidity. Actually both are same. Okay, both are just the synonyms of each other. Now if you see that, let's say, for example, I'll just draw this a little aside so that it would be a little easier for you to understand. Now if I want to give certain forces here, so let's say, for example, if I give a particular force here, I'll just draw it with a little darker pen. So if I give a force here, actually you will get the resultant at this point. Why? Because this is the stiffness center. All right, this is the force center, this is the stiffness center. So in this case, what happens, actually, you will get to know certain delta bending moment, which is a torsion. All right. So let's say, for example, I'll call it as delta, let's say delta 1 instead of x and y. All right. Similarly, if you apply the force in the other direction, let's say, for example, I'll just take the different pen color so that it is easier for you. So if I apply the force here, similarly, you will get the reaction in this case. So in this particular case also, you will have a particular effect, which is, let's say, delta 2. This is delta 1 and this is delta 2. So let's give certain figures actually over here. So let's say, for example, this one is, let's say, EX, which is earthquake force in X direction, all right? And this is, let's say, EY, which is earthquake force in Y direction. So what happens is, when it comes to the numerical equations, you will see that delta EX multiplied by, this is delta 1. Okay, this would be the torsion. Is it the, what kind of torsion? It is the actual torsion, I'll just say. Okay. Apart from this, you will get the accidental torsion. What is meant by accidental torsion? Accidental torsion means, let's say, for example, imagine that this is, your floor plan of, imagine that your father is running a grocery business here. And at this particular place, due to corona or whatever the situation is there, actually, he put up some very heavy material there, stocking the material, or let's say gehu, jawar, all that thing actually, because it is rice, for example, because it might be needed and you don't know when the next time the delivery it is. So what happens is, certain, actually the center of stiffness doesn't change, this guy doesn't change, But this guy, which is the center of mass, it changes slightly towards this side. From what? Accident. So this is the accidental torsion that you are saying. What is accidental torsion? What is the distance actually? The distance, what we call it as a calibration. So let's say, for example, this is the B into 0.05. 5% it's the accidental torsion. So whenever you are applying the force, Ex multiplied by delta 1 is the actual torsion plus 0.05 times the B. This is the B. You take as Bx here and take the By here, or vice versa. You can name anything there. I'll just take the 0.05 times B. Actually, we'll take this plus and minus because you need to take the worst load combination. Sometimes it is this side, sometimes it is this side, right? So this side it will be plus, this side it will be minus. So we'll take either plus or minus times 0.05 times B actually, and this also will be multiplied by again the Ex. Alright, so this is, we call it as the actual torsion. This is accidental torsion. Right, so I'll just take it this side so that you can see this. Alright, so you can see that you will see the delta x multiplied by Ex multiplied by delta 1, which is the torsion, and you will get the accidental torsion. Because of that, what will happen is this building will try to tend to move to that side. So let's say, for example, I'm having a laptop bag. I'll just try to strain myself to that side. If I don't give the equivalent force, imagine that I'm holding a laptop bag here. Let's say 2 laptops in a bag. What will happen? I'll start moving in, deflecting in that direction. I need to, my muscles has to give a lot of strain to balance the equation. Otherwise, I'll fall down. If I faint, actually, I'll fall down. All right. If I don't balance the equation, what will happen? I'll fall down. Right. I don't want to do that. I don't want to. The building doesn't want to fail down. Right. So it has to give that kind of stiffness. All right. So how much that would be? Okay. That depends upon how much amount of torsion that it is happening. Alright, so is it only due to the horizontal force of earthquake or something? No, it might be due to its own weight. Let's say laptop bag is not somebody is pushing me from back. Alright, so what happens is it is just due to the laptop bag. It's additional weight. It is just due to maybe this material that is stopped. No horizontal force. The vertical force is getting deflected. Alright, so what happens is this is not the linear behavior. This is something which is non-linear. And what is non-linear means? It is due to the self, it is because of the self weight. Imagine this guy is holding a laptop bag here and this guy is deflecting. The building is deflecting. Alright. So since it is deflecting, you will see that there is a delta, and due to that there is a non-linear geometric P delta effect. Alright. So is it linear? No. Big no. Right? It is a non-linear behavior. Is it studied in the college? No. Unfortunately, it is only through certain equations and all actually, but the practical numerical problems actually we couldn't get a chance to go through that because it's little complex. How it is complex? Let's look into it. So let's say, for example, I'm having a building here, I'm having, let's say, the mass here. Actually, this will get deflected due to the center of mass shifted. Right, so this is mass. I'll take this as a particular force here. I'll take this as a P as a force. M is the mass. It's okay, but mass is required for the horizontal accelerations and all also. But I'll take this as a P to make it a little simpler. So same P, it is getting deflected like this over here. So this is P1 multiplied by delta 1. Because of this, actually, again the second order bending moment will start, and you will see that the deflection has increased due to the P1 into delta 1. Understood? Again, due to P1 into delta 1, some more deflection will come. Maybe I'll take some different pen. It is like this over here. So again, this will be P2 into delta 2. Again it will be some more, it is P3 into delta 3. Understood? So up to what extent you can go? P1 into delta 1. So let's say for example this is P2 into delta 2, P3 into delta 3, where it is going. So it will stop with certain value, we call it as the iterative process. Somewhere it has to stop. All right. So when it comes to the analysis, actually, I'll just unlock this. You will see that there is a convergence tolerance, that now this is it. All right. So somewhere we need to stop it. So this is the tolerance limit. All right. To this extent, once the deflection comes up, the equation will stop because the resultant is barely nominal. You can just skip it off. It will not make a huge difference to the equation. All right. So this is the tolerance limit actually. That's what actually we will be seeing it into the P delta analysis. All right. Is it really important? Yes, of course. All the buildings actually. You will see that this is the project in which, can you guarantee me that, the center of mass and center of rigidity is exactly at the center? No way, right? All right, so I'll just take the pen up. In this case, it's not guaranteed that you will see both the things together. There might be the center of mass would be somewhere here, center of stiffness would be somewhere here, and because obviously that actually some kind of bending moment will start. All right, so it is not guaranteed that you will have the proper, there is a, it looks similar actually, but this is the lift core, this is the lift, or this is another lift core, this is the staircase, this is another staircase, but you will have different configuration over here, right? You cannot see that it is exactly same, and plus there is a curve, it's not a straight line. So complexity will go on increasing, my dear. All right. So it's very, very important for you guys to understand that this is never ending. What you need to do is you need to manage the equation with what? With the numerical problems. So that's why various different analysis you have to do it. Not only the linear static, also along with that the nonlinear geometric nonlinearity with the P delta, buckling analysis. What is buckling analysis? Let's say I give you one punishment to just stand up. Can you please stand just for a minute for me? Yeah, please, thank you. Sit down. Now, it is just for a minute, so it's okay. If I make you stand for 2 hours, still okay. 2 days, will you really stand? Come on. But the building stands throughout the life of the structure. Don't you think that you want to sit down somewhere, for God's sake? Don't you think that the building wants to sit down? Can you let the building sit down like that? No. Continuously the forces are coming through the gravity and all, unlimited, and till the life of till the building comes down to the gravity, it is just the war is happening. The gravity, resultant forces. It's a buckling analysis, right? So due to its self weight, actually, if the structure is getting buckled, it's a buckling analysis. You will see the buckling analysis if the structure is tall enough, quite a tall and a stiff, very tall structure, standing. Imagine that your legs are you are heighted like giraffe legs, and the strength is not like giraffe, maybe like human. You'll see that the legs are paining tremendously, surely, right? So that's the buckling analysis. Is it really real? Yes. If it is not real, just stand for a day and your legs will tell you, come on, I'm buckling, please sit down. All right. Okay, so this is the buckling analysis. When to do, how to do, what to do, where to do, how to check. All these types will be there. Somehow actually we have to cover so many different types of analysis. So we may not be able to go to those areas. But P delta analysis is, I just wanted to tell you that these are the real types of analysis. In the college days, actually, we have just studied the linear static analysis. It's of, I mean, I'm not saying it's of no use. I'm just saying that this is not enough. All right. So next one is pushover analysis. Pushover analysis, how far to push over. What is that? No, you're doing some yoga or something, stretching. Do like this, something. Okay. So let's say if I want to do like this, how far I can go back? I'll just go down like this, like an arch. Can I go arch and come back again go back? It's impossible. Come on, my spinal cord will start. My God, I can't imagine also. So what does that mean? How far you can push? Pushover analysis. Push over. Is it over? Not over. Again push, again push, again push. Till the time, the structure says now this is enough. That is a pushover analysis. Is it required? Yes. To calibrate the strength. Let's say, for example, this mobile. I want to check how far you can throw it down and it's still okay. How far I can put this in under the water, still it's okay. Pushover analysis generally used for the buildings to find out the performance of the structure. Please understand. Please, the curly bracket. Come on, one more time. Performance of the structure. All right. Now, what do you mean by performance of the structure? Let's say, for example, this is a mobile. I put some case on this. Why it is for that? If somebody by mistake, if it is falling down, actually, mobile should not get crashed. Everybody uses that, right? You need to protect it. The cost of the mobile and cost of the, let's say, the screen guard or something, whatever the accessories that you are taking, is it comparable? No, come on. The mobile will be in the range of 50,000, 80,000, something like that, or maybe 1.5 lakh rupees. But if you see the screen guard, actually, it might be some 5,000-10,000 maximum. Right? Not even 10%, but it is needed to escalate, to increase the lifespan of the structure. That is the pushover analysis. Is it required? Yes, definitely yes. To understand the performance of the structure. Understood? Right? So this is this the static analysis? Everything, boss, is in the static analysis. We'll come to the dynamic analysis after a while. All right. Then what is the creep, shrinkage, and material strength? Creep analysis is like, oh no, I'm feeling like creeping. What is this? What does that mean? It's something like constant, the pressure, tension, that particular action will lead for you for creeping. What does that mean? I'll give you the practical problems. All right. Imagine that you are going through a bridge, for example. In India, we don't know the design more than a simply supported design. Okay. The bridges are only simply supported. This is not a continuous, there is a break in between. So what will happen? Every bridge is the simply supported. So WL square by 8. Maximum deflection is at midspan. So whenever the vehicle is there, imagine that you are going through a car or a two-wheeler or something, you will get some dig kind of sound. Have you heard about it? I'm sure you are. Later on, when you go through a vehicle, actually, you will see the difference. You will say dig like that. Why? Because there is a maximum deflection here, zero deflection here. Maximum deflection here, zero deflection. Maximum zero, maximum zero. So what is that? Creep. This decking is a big load. It will give you the some kind of strain, means the deflection. Permanent strain is a deflection. It's a cramp, right? It's a deflection that is happening. Who is going to support it? After, let's say, 50 years, actually, the bridges got constructed. All the politicians, all people will come. I'll hold you. Thank you for giving the service for 50 years. Is it possible that way? To give you the support, it's impossible, right? It's impossible. So the self-weight plus the vehicle load, it's going continuously, increased in the vehicles. Tippers will go, trailers will go, day by day the population is increasing, so obviously the load will also get increased, right? So if you see that this would be the maximum deflection, zero deflection, maximum deflection. So if you see what is this maximum deflection, the linear elastic deflection will go back once the vehicle is there, but still the self-weight is there, it's not gone. Due to the constantaneous torture, you will get the cracked deflection, and due to continuous action, it will be having the creep deflection. Creep. Right? This is like a young boy. This is like a little mid-age person, and this is the old age person. Creep analysis. I hope you are getting what I'm saying. Right. So is it really happening? Are you designing the bridge for a day or two just to freak out? No, right? Is it for a year or two? No, right? It is for generations to generations, right? It is for you, it is for your father, for you, for your son, as long as it can. All right. So creep analysis, is it really a real type of analysis? Answer is yes. All right. Are we doing it? I haven't heard about it. All right. So is it possible in Indian code? Yeah, there are 3 lines given in the code with the creep coefficient and all. Is it sufficient? Answer is big no. Then what code you will be using? ACI 318, American Council, then CBFIP code, Euro code. So such kind of codes are required to deal with this type of analysis. Again, is it a required? Do you want to die in the young age? Come on. Do you want to die as a kiddo? No. Not as a younger age? No. Just you got married and you got died. Is it okay? Is it a good life that you lived with? No, right? You want to die and get older. Am I right? That's a full-fledged life. Similarly, the structure has to have full-fledged life. Am I right? Come on. Right? So creep analysis is a real type of analysis, and it is must. It has to be done. So what is this code all about and all? Actually, just Google it out, CBFIP code. It is half of the telephone directory. I will not be able to take such kind of things, but it is really needed. Through the software, the life is a little bit more easier. Let me show you a few things actually. If you go here, let's say M40 or something, actually, you can go to the time dependent properties and you can give this creep analysis. This is what I was talking about. CBFIP code, ACI, Australian code. This CBFIP, the latest version. This is the Euro code. This is the New Zealand code. Where is the Indian code? Ooh, there is no Indian code. If you guys are doing PhD, please do this in this. Get some user values, get some coefficients and all. PhD, you'll be a doctor, somebody. Right? Why? Because it is really needed here. The creep analysis. We don't have the Indian coefficient somehow. Alright? Got it? So CBFIP code, which you can use it, you can give certain cement type factor, relative humidity factor, and certain creep coefficients. You will get certain graphs like this, and you can complete the entire creep analysis. And you can find out basically how much is the creep after, let's say, 10th day to this day. And you can get this figure. The software will add these figures right for you for this particular concrete when you are using over here. That's how actually the creep analysis can be done. What about the shrinkage? Is it needed? Whenever you're pouring the concrete, it is there in the semi-solid or semi-liquid kind of form, right? So it already the drill that heat of hydration will come, it will come consolidated and all. Actually, there would be again more heat of hydration will come, and it will start to binding in. There will be initial setting time will be there. If it is not, creating the conducive equation, actually, it will create a crack, which is called as the shrinkage crack. Immediate concentrated crack in the concrete is due to the shrinkage. Right? Don't get panic with this. right? There are so many options are there where you can get rid of this shrinkage. But is it really good for the structure? Answer is big no. It will crack. Any non-engineering crack is a failure. Come on, say with me. Any non-engineering crack is the failure, right? What is the engineering crack then? Expansion joint, construction joint is engineering crack, engineered crack, right? I'll tell you one more example, engineered crack example. Let's say this is the satellite. I'm very bad at creating the drawings somehow. This is a satellite. ISRO, NASA, all people put billions and billions of dollars and Econstruct, Sandeep Pingale is designing the support conditions for this, and the satellite has started. And says Sandeep Pingale, mentors of structural engineers, they put this. The satellite is not going. Oops. It is designed by me. Come on. Satellite won't go. Full tight. Is it a good design? Hopeless design, right? At certain thrust, once the satellite actually gets to the torque, actually it should get broken and satellite should go. That's the purpose. It's a creep analysis. At what time, at what thrust, this guy gets collapsed. Right? Is it really needed? Answer is yes. Answer is big yes. Where it is needed? Many places. I have given you few examples. You can figure it out later on. Compressive strength. Definitely needed. 3 days of cube testing, 7 days cube testing. We do it every day. Every concreting. 3 days, 7 days, 14 days, 28 days. Compressive strength. Is it really getting that much amount of strength? Compressive strength, that is actually the material nonlinear analysis. Alright, so we have studied this static analysis. Now similarly, what is dynamic analysis? What is the difference between static and dynamic analysis? Imagine that you have proposed to a girl, or if you're a girl, you're proposing to a boy. And the boy is saying, something, or a girl is saying something like this. Then there is a chance that the answer might be yes. But in a big slap, answer is big no. Correct? Okay. So one type of analysis actually like this, static analysis. Another one is the dynamic analysis. Force is same, effect is different. Do you agree? Somebody is pushing you from back and somebody is kicking you from back. Your reaction is different. You want some more examples? I'll give you one more example. Imagine that this is a nail. This is my digital pen, but I wanted to give you one example. Imagine that this is the door. If I put the static force over here, will it go inside? No. But if I put the dynamic load by taking the hammer like this, will it go? Yes. Same force with the dynamic in nature. It works differently. Right? This is the difference. Is it really needed? Of course it is needed. Earthquake, do you think that earthquake is coming? Oh my dear buildings, I'm waiting for you. Will it come like this? No, it's a big slap to the structure. Khada. Correct? Dynamic analysis, definitely needed. Linear dynamic, yes. There is a non-linear dynamic also. Oh yeah. Okay. In the linear dynamic, what all the different types are there? Response spectrum analysis, modal analysis, time history analysis. What is response spectrum analysis? There is a spectrum curve is there actually. I don't know, most of you might not be knowing. There is a response spectrum curve like this. It goes to the infinity. This is SA by G. This is the time period, which is the approximate time period. Right, and this is actually, what is SA by G? Spectral acceleration with respect to the gravity. Do you think that during the event of earthquake, gravitational force is zero? During the event of earthquake, gravitational force is zero. Come on, impossible. Otherwise, all will be there in the space. Gravitational force cannot be zero. But how much more is the gravity that is acting? That is actually S by G. Is it really weird to understand? I would like to tell you one thing. Imagine that you are in the class. I am also there as your friend in the class, and I put some, let's say, iPod plug in my head. I think I don't have it here right now. Okay, imagine that some iPod plugs are there in the head, and I will say all of will look at me that what the heck is this guy? Yes. Everybody is experiencing some kind of atmosphere, and this guy is experiencing something more. That's what it is. Every building is experiencing the gravity, but the certain part of the earth is experiencing a little bit more. How far more is the earthquake force? How far more is the S by G? Right? So this is basically the response spectrum. Okay? Modal analysis. What is meant by modal analysis? आज मेरा मूड नहीं है पिक्चर देखने का. Come on. Okay. What do you mean by modal analysis? First mode, second mode, third mode. Right? Different modal analysis is there. I think I have created a beautiful video here. Actually, this is the video. It is there in our YouTube channel. Please subscribe it and go through that video. You will find out very important features about the modal analysis. Those who don't want to watch, I will just give you a glimpse about it. First mode, second mode, third mode. Whenever the earthquake comes, imagine that somebody comes and slaps you. What you will do? Kill him? Beat him? You will give one more slap? What is the behavior? What is your nature? You'll go to the police, you'll go to the headmaster. What you will do? That depends upon your individual behavior. That is the modal analysis. The modal analysis will tell you the behavior of the structure. This is like a psychology. Right? You will understand the psychology of a person. You will understand the psychology of the structure. It's very important to you to, if you are a doctor, you must understand the psychology of your patient. Similarly, if you are a structural engineer, you must understand the psychology of the structure that you are dealing with. And this very modal analysis will tell you like this. Imagine that you are proposing a girl, Atika Khandala. If a very big slap is there, answer is big no. But if the girl is saying that my father is not at home, there is a homework, what I do, there is a chance. We call it as mixed mode. The chance is yes, first mode or second mode. Might be interchangeable. Behavior. Understood? But in the structure, we require the distinct behavior. Right? Is it really needed? Of course it is needed. Modal analysis. If you don't understand the behavior of the structure, what the hell you can design the structure, right? Modal analysis. Next one is time history analysis. What is time history? Oops. What is this? Earthquake. This is the time domain and this one is the displacement. At what time, how much amount of displacement is happening? This is the time history analysis. Understood? So what is the difference between this and this? Time history and this analysis. There is a synthetic earthquake and many things are there actually. I'll not go too much deep into this, otherwise you will get headache about it. But all the earthquake forces are enter this, and from here to here there is a inverse Fourier series transformation that will happen to form this particular curve. This and this is same only, right? So the difference between time history and time history is more accurate. Why? Because it is complied with, let's say, time history of the Bhuj earthquake, time history of the Nepal earthquake or some Killari earthquake. But this response spectrum is like from the entire India, it is one graph only. It is like a standard, right? So both the types of analysis are related to the dynamic analysis, modal analysis also I had told you. Are these only the types of analysis? No, my dear, there are many types. Okay, I have just covered these ones. If you want to hear the other types, actually, there is a nonlinear analysis is also there, which is covered to the response spectrum model and this, which leads to the very beautiful concept, which is the PBD, performance based design. Okay, which comes with the nonlinear time history analysis. Do you want to see that? If you go here, you can add a new function, which is response, the time history analysis, which is FNA, fast nonlinear analysis. And you can add certain values here, which might be the static or maybe accelerations. You can add the functions also. And this nonlinear FNA time history analysis would help you to give the performance checks, right? So is it needed? You don't want to see the performance of the building? What is the cost of the mobile? 50-80,000. What is the cost of your car? Maybe 5 lakhs to 10 lakhs. What is the cost of your house? Might be in crores. If 80,000 is your let's say the mobile cost, you will be living in 1 crore villa or an apartment. Don't you want to see the performance? If you want to see the performance of this mobile by putting the cap on this, you don't want to see the performance of the building. So is it needed? Of course it is needed. You don't realize it is needed. All right. So all these types of analysis are required to satisfy the building stability, performance, durability, and the the serviceability and strength criteria and all. Right. So when to use this type of analysis, I've given you the different equations, different examples. I'm sure that you would have really liked it and loved it. If you really liked it, please give a thumbs up. If you really loved it, please subscribe the channel. And please make sure that you will come to the next time 12W, 12M sessions, 12 webinars in 12 months. Right? So if you are having any sort of doubts, please add it in the chat boxes. I'm recording this session a little earlier. All right. So I would be, chatting with you, giving the answers there during that time, because I want to be with my family during this 31st of the December, and hopefully the next year will be, out of Corona. Hopefully, I'm putting my fingers crossed, and I would like to wish you a very, very happy new year to everybody, to yourself, your family, with everybody. And I'm sure that those who are at final years, I'm sure that you will be getting the jobs in the core technical. Please make sure that you will be getting the jobs in the core technical. Apart from the core technical, if you go to somewhere in the chemical engineering, somewhere in the call center, somewhere in the software and all, actually you'll earn the money, but satisfaction will be zero. Please give a sincere chance to your own career, to your own branch. And if you fail there, then you can move around to another fields. But just, you are from BTech, from this university, this college and all, actually, if you are getting a job in somewhere in software testing and all, please, life is quite better than that. Right? So many new AI tools are coming to replace you guys. Don't get trapped into those areas. Okay, civil engineering is a very classy, magnificent line actually. Okay, and you can definitely join that line and make a career of this. I'm really enjoying my line, with the fullest of my heart. Right? So thank you very much and see you next year. Bye-bye.